we will start classical field theory. Quantum field theory is more complicated because of uncertainty relation, the Lagrangian operator, destruction operator, but classical fields we do not need any of it. Okay. So, there is a field variable and we can define Lagrangian equations and so on. So, that is what we will start with. So, we have field phi x t. So, it is function of position and time, like a string, this string is there, this string. So, for this x, for every position at given time I have amplitude. Okay. So, I can treat that as a field variable. Okay. Pressure field in this room, any position there is a pressure. Okay. So, we have this field. Now, so for a string there are derivations, but I think we will skip the derivation, but we can define kinetic energy as a, so every the string is, there is a mass element, no, this is the mass here, and that mass is changing with position, with time, its position is changing with time. So, it has kinetic energy half m v squared. So, half m is basically rho times dx is mass and v squared, that is velocity. Velocity is only along z direction, and these formulas are useful only for small amplitudes. For large amplitudes and nonlinearity comes into play and formulas are different. Okay. So, for small amplitudes these are good formulas. We can define potential energy. So, potential is okay. So, you can, it is kind of elastic energy. Okay. So, if it goes up, then it's elastic, well it tries to come back. So, that is like in fact more like oscillator. So, it is a d phi by dx. Okay. So, the derivation I will not do it, but we can in fact again find it in internet or in books. So, d phi by dx square dx, kappa is like a spring constant type thing. So, it is a elasticity coefficient. So, kappa by 2. Now, so we can define action similar to what we do for particles. So, action will be, which is function of phi of x t, t minus v is kinetic energy minus potential energy, and so now there is a dt, right. I mean this of course start from t1 to t2. Now, this t and v are function of these functions which are already integrals. T and v are integrals. So, I get dt and dx and these are the functions. Okay. Now, so we have in particle dynamics we had only integral dt. Now, we have dt dx in 1D, but in 3D it is going to be dx dy dz. So, in 3D we will have 4 dimensional integral dt and 3 space dimension, and this L, this kind of this L, math L or curly L is called Lagrangian density. Okay, it is called Lagrangian density. Okay, and this is integral t minus v dx. This is Lagrangian. Okay, it is like before. Okay, but I have integral dx. Okay, because it is a field. For particle we do not need dx integral because it is a delta function object, right, mass. But here I have this is Lagrangian, but without dx it is a Lagrangian density. Okay, so Lagrangian density is this half rho dt dx squared minus half kappa dx d phi squared dt d phi. Okay, so this is the Lagrangian density. Now, in fact, we can derive equation of motion by, we had equation of motion for particle as mx double dot is minus v prime. So, similar equation can be derived by Euler-Lagrange equation, or we can derive Euler-Lagrange equation by minimizing action. Okay, now, we need to put all those formalism. So, extreme condition. So, I had defined action with dt dx that. Okay. Now, I want action to be minimum for a, so for the field trajectory for which action is minimum is the classical solution. The way we have classical solution for particles which minimizes action, here also we will get a field configuration as function of time. Okay. So, for string it does oscillations, no, like goes back and forth like that. So, that solution is a, for that solution my action is minimum. Okay. So, extremum condition for action will give us the equation. So, delta is delta phi 0 and okay. So, extremum condition derivation is very similar to what we did for particles. Okay. Now, for particle we had d by dt partial L partial x dot, no, that was what we got. Now, instead of x dot we have fields. Okay. So, derivation is very similar to what we did before. This x dot will be replaced by delta t phi. So, this is delta t phi, right. So, that was position time derivative. Now, I have field time derivative which is with relative to time. So, this part you can see that it is looking similar to particle time derivative, but it was only dx by dt that time, right. X was only function of time, but this x is replaced by phi. Now, phi is function of x and t. So, I will have d phi dt and d phi dx, two of them. So, this is the second one with relative to x. So, Euler-Lagrange equation for fields is this. Derivation is exactly same as for particle, but of course, we are constraining that the fields are constrained, they do not change at t equal to 0 and t final. So, remember for particles we say dt Lagrangian t1 to t2, the position of the particle at t1 and t2 are fixed, right. We do not change the field at the end points. Similarly, also the constraint here, the fields are not changed at time t1 and t2. Okay. So, if you put that constraint like what we did for particles, we will get this. It is more algebra, but on exactly same lines. In fact, you can see the motivation why these are coming. Okay. So, this is Euler-Lagrange equation for fields. Euler-Lagrange equation for fields. Okay. We need it, so I think you need to memorize it. You can see the form which is this is like dl by dx. So, instead of partial L partial x, it is partial L partial phi. Then we have d by dx partial L partial of phi x. These are derivative with relative to x, and then we have partial L partial with phi derivative in time, and then d by dt. Okay. Now, let us apply it to our string. This is my Lagrangian density. So, what about partial L partial phi, this one 0, no, it is not a explicit function of phi, 0. What about this one, partial L partial dx phi. So, take this Lagrangian and take derivative with relative to partial x phi. So, which part is partial x phi? This is partial x phi. If I take the derivative, what will I get? 2 will cancel with half, I get minus kappa dx phi. Dx phi. Okay. Dx phi is a function and I am just taking derivative to dx phi. Okay. Now, what about partial L dt phi is going to act on this, and again same thing rho dt phi. Substitute it here. So, the first term is 0, second term will be minus becomes plus kappa, double derivative d by dx is coming on that. So, d by dx phi. then the second one is d by dt is coming. So, this will be minus rho d square phi dt square is 0. Okay. So, and that is our, well, that is exactly the same what I wrote. So, that is the equation of motion. Okay, this is a wave equation, okay, for string. It is a linear equation which is valid only for small amplitudes, otherwise nonlinearity will come, and great. So, we can derive equations of motion for waves or for classical fields once we know the Lagrangian. Okay. So, for lot of fields we, well, most of the field theory we take Lagrangian, we assume existence of Lagrangian, but it does not work for Navier-Stokes equation. It is dissipative, Lagrangian is not well defined. Okay. We can do some trick, but it is not that Lagrangian is there for all fields, all field theory.